In this video, we'll cover three concepts. First, we'll talk about the fundamental counting principle. Then we'll talk about two other ways to count events, and those ways are permutations and combinations. And we'll give examples of each of these so that you'll understand them. So the first thing you need to understand is something called the fundamental counting principle. If one item is chosen from a group of m items, and a second item is chosen from a group of n items, then the total number of ways a two-item choice can be made is found by multiplying the number of choices for the first item m by the number of choices for the second item n. So remember, we're making two choices. Our first choice has m possibilities. Our second choice has n possibilities. And if we're going to choose one from each of these groups, we multiply m times n. So here is an example of the fundamental counting principle. And the reason we know that this is an example of a fundamental counting principle is we have two choices here. Choice 1, choice 2. So let's read the complete problem. A restaurant offers combo meals. You can pick from 4 kinds of salads and 3 kinds of sandwiches. How many different combo meals can be made if you have to pick 1 salad and 1 sandwich? So our first choice is one of the 4 salads. So m equals 4. And our second choice is one of the 3 sandwiches. So n equals 3. Now, according to the fundamental counting principle, we just multiply these two together, and our answer will be 12. So let's look at what those 12 choices are. If you select this first salad, you can then select any of these 3 sandwiches. That's your first set of choices. There are 3 ways to pick this salad with these 3 sandwiches. However, you may pick the second salad. If you pick the second salad, you can pick any of the 3 sandwiches. Well, that's again 3 combinations. Now you can see what's going to happen here. We're going to repeat this process for every one of these salads. And so each time there are 3 choices. And that's where we get 4 times 3 equals 12. So using the fundamental counting principles, we just look at the first choice. We find how many ways we can make our first choice. We look at our second choice. We multiply those together, and we get the total number of choices that we can make. That's the fundamental counting principle. Now, this fundamental counting principle can be extended to more than 2 items. So you may have more than 2 choices. You might have, with that salad, you might have had a dessert. And the way in which a series of successive events can occur is found by multiplying the number of ways in which each of the events can occur. So here's an example with more than 2 choices. An ice cream shop offers 20 flavors of ice cream. First choice, flavor. 4 kinds of cones and cups. Second choice, cones, or cups. There's only 4 ways to do that. And 4 toppings. Last choice is a topping. So we have 20 ways for the first choice, 4 ways for the second choice, 4 ways for the third choice. So the total number of ways we can make our ice cream is 20 times 4 times 4. That is a total of 320 ways. Now you can extend this to 4 choices or 5 choices or 6 choices, assuming that you're only selecting one from each of the categories. So we're not picking 2 flavors of ice cream. We're just picking one of the 20, one of the 4 toppings, and one of the 4 cones or cups. So that's what makes it the fundamental counting principle and makes it different from the permutations and combinations we'll talk about, and that is the selection of one choice from each category. Here's another example. The choices for a hamburger are as follows: 5 kinds of cheese, with or without mayo, with or without mustard, with or without ketchup, with or without tomato, with or without onion, with or without bacon. How many different burger combinations are there? So our first choice is cheese, and we have 5 kinds of cheese, and we're assuming that we do pick one of these 5 kinds of cheese. Now, with or without mayo is really only 2 choices. With mayo is a choice, without mayo is a choice. So, have 2 choices for the second category. With or without mustard, that's 2 choices. With or without ketchup, that's 2 choices. With or without tomato, again, 2 choices. With or without onion, 2 choices. And with or without bacon, 2 choices. So in order to find the number of ways to make our cheeseburger, we multiply 5 times, and I can write this as an exponent, 2 to the 6th. Now you could just simply multiply 5 times 2 is 10, times 2 is 20, times 2 is 40, times 2 is 80, times 2 is 160, times 2 is 320. Or you could take out your calculator and do 5 times 2 to the 6th, which is 5 times 64. That will also come up to 320 ways to build the burger. Again, just multiply on your calculator from left to right, or if you'd like to rewrite it with the exponent and enter in your calculator 5 times 2 to the 6th, it will do the order of operations for you first and do the 2 to the 6th. You'll get 64 times 5 is 320 ways to make different burgers. Now, before we talk about other ways of counting things, we need to talk about a concept called a factorial. In a factorial, we're going to take a number, like you see in the example here, 5, and we're going to follow it with an exclamation point. This notation means you take the number and you multiply the number times 1 less than the number, 2 less than the number, 3 less than the number, and you keep going until you get to a last factor of 1. So for 5 factorial, that means we start with 5 times 4 times 3 times 2 times 1. So if we had 4 factorial, we would start with 4 times 3 times 2 times 1. 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1. So the notation of the exclamation point simply means start with this number, count down by ones, multiply those numbers together until you get to the value 1. Now you could take your calculator and multiply these out. 5 times 4 times 3 times 2 is 120. 4 times 3 times 2 times 1 is 24. And 7 times 6 times 5 times 4 times 3 times 2 times 1 is 5,040. And so you can see these numbers get large very quickly. Now, it's also important to know that 0 factorial has a value of 1. And that's very similar to when we say we raise a number to the 0 power, we get a value of 1. This is just by definition, and you might encounter this, but most likely you will not. So now we're going to talk about a kind of counting known as a permutation. And it's a different way of counting the occurrence of events or items together. In the case of a permutation, each event can occur only once, and the order of the occurrences does matter. So, for example, when we see something like BA, that is not going to be the same as something like AB. It's probably clear to you that these are different, but if you were talking about getting ice cream on an ice cream cone, and you had 2 scoops on your ice cream cone, and you had flavor 1, flavor 2, you probably wouldn't care what order those 2 flavors are on those cones. So 1, 2, and 2, 1 would really not matter in the case of an ice cream cone. But in this case of letter BA and AB, those are considered different in a permutation. The formula for finding a permutation has to do with those factorials. And that's why we talked about what 5 exclamation point or 5 factorial meant. So here's the permutation formula. The permutation of n items taking r at a time is n factorial over n minus r factorial. So let's look at an example, and then we'll talk about a shortcut for this. Here we have the example of the vowels A, E, I, O, and U. How many different ways can 2 letters from this set be arranged? Now, according to our formula, that would be 5 objects, A, E, I, O, and U, 5 different objects, and we only want to select 2 of them. According to the formula, this will be 5 factorial over 5 minus 2 factorial. So in the numerator, the total number of objects you have. In the denominator, the difference of those objects factorial. Now I'm going to show you a shortcut for doing this, but let's go ahead and work this out. 5 times 4 times 3 times 2 times 1. And all of that is over 3 factorial, since 5 minus 2 is 3. So in the denominator, we've got 5 minus 2 factorial, and that's 3 factorial. So in the denominator of this fraction, we would have 3 times 2 times 1. And just with regular fraction division, you know, you can reduce these common factors from the numerator to the denominator. So our answer here would be 20. So there would be 20 different ways to arrange these vowels. Now you can think of this sort of like the fundamental counting principle, because if you say you've got 2 choices here, your choice for the first letter is 5. You've got 5 choices. You can select A, E, I, O, or U. And your second choice, you'll only have 4 choices. Because if you select one of these, say for example we select the A, well, we've already selected the A, and that leaves us with only 4 letters to choose from in the second. Because unless they tell us otherwise, we can't repeat letters. So it turns out to be, you could just say 5 times 4 is 20. So you start with the total number of items, which is 5, and you need to make 2 selections, so you reduce by 1 to 4, and that's where you can also get this answer. It will always match with this factorial formula, but this is sort of a shortcut to the same kind of problem. It's a little bit easier than memorizing the factorial formula. Here's another example. One episode of a game show has enough time to allow 5 contestants. These 5 contestants will be selected from 12 who have been selected. How many possible ways can the 5 selected participants be selected from the 12 who are eligible to be chosen? This is a permutation. 12 people choose 5. In this case, we are concerned with the order. So if you've got Mary, Tim, Sal, John, and Jose all participating, that would be different from Tim getting picked first, followed by Mary, Sal, John, and Jose. So we're saying that order does matter here. Let's go with the formula first, and then we'll go with a shortcut. 12 factorial over 12 minus 5 factorial. That's 12 factorial over 7 factorial. That's 12 times 11 times 10 times 9 times 8 times 7 factorial. I'm not going to write 7, 6, 5, 4, 3, 2, 1 because I want to divide that out with the 7 factorial in the denominator. And now you can see why that shortcut formula works. Because look what we have here. We have 5 selections to make. It's like the counting principle. The first selection, we have 12 ways to make it. Once one of the contestants is picked, we only have 11. Then we have 10. Then we have 9. Then we have 8. So here's the 12. You start with 12, and you basically have 5 choices. So you go down by 1 5 times. To get your final answer, of course, you have to multiply this out. 12 times 11 times 10 times 9 times 8. And this is a very large answer because we have a lot of people. It turns out that there are 95,040 ways that 5 contestants could be chosen from 12. Now, I've only written 5 names, but there are technically 12 names, and 5 contestants are pulled from those 12. And there are 95,040 different ways those contestants could line up for the game show. Now, sometimes you'll be asked to look at a permutation with identical objects. And when objects are identical, that means they've repeated themselves, and that's going to lessen the number of ways that you can arrange them. So I'm going to start with a simpler example than addresses because that's got a lot of letters in it. Let's just start with the letters of the word B-E-E, B, like a bumblebee. If I was going to figure out all the ways that I could arrange these 3 letters, I would get B, E, 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 B, or E, B, E. So there are 3 ways to arrange this. Now, there are no other ways that I can arrange all 3 of these letters. Let's look and see if that holds true for the factorial formula. So our n here is 3. We have n objects, B, E, E. So our numerator is 3 factorial. Q of the objects are identical. Well, Q, in this case, identical. There'd be a B that's identical. And then R items are identical. That would be E, could be R. So 1 factorial, since there's 1 B, and 2 factorial, since there are 2 E's. And since the value of this is 1, we don't really have to write it. We really only have to write the ones that are the same. That gives us 3 times 2 times 1 over 2 times 1. And that's our 3 ways. And we see our 3 ways here. So when you have more letters, obviously you don't want to have to write them all out, although you could. So we've got the letters of the word addresses. Now there are a total of 9 objects, 9 letters in this word. But we've got some repeaters. We've got 2 D's, that's 2 factorial. We've got 2 E's, that's 2 factorial. And we've got 3 S's, that's 3 factorial. So the number of ways that we can arrange the letters of the word addresses is 9 times 8 times 7 times 6 times 5 times 4 times 3, 2, 1, which is 3 factorial. I'm going to leave it that way so that I can divide out this 3 factorial with this 3 factorial in the numerator. You could write 3, 2, 1 and write the denominator as 3, 2, 1 and then divide them out. 2 factorial is 2, and because that's 2 times 1, and another 2 factorial is another 2. So this is 2 times 1 times 2 times 1 in the denominator. That's really 4. So we could take these factors and divide out the 4. So what we really have is 9 times 8 times 7 times 6 times 5. So when we multiply that out to find out how many choices we have, because there are repeated objects, we still have a lot of choices, 15,120, but not nearly as many choices as we would have had if all of these letters had been unique. So you want to make sure that when you have repeated factors that you follow this formula. Total number over the factorials of all the repeated objects. In permutations, we saw that different arrangements of letters, different arrangements of people were considered to be different. But in combinations, they are not considered to be different. So when you're working with a permutation, AN and NA are 2 different things. But when you're working with a combination, we say that AN and NA are the same. So for example, a quarter and a nickel. If you have a quarter and a nickel, it doesn't matter if you have a quarter and a nickel or a nickel and a quarter, you still have 30 cents. So we can go back to the ice cream example. If you have 6 flavors of ice cream that can be chosen for an ice cream cone, how many different flavor combinations are there for a 3-scoop cone? Now, it doesn't really matter which scoop goes on the top, in the middle, or on the bottom in this case. If you go up and you order strawberry, chocolate, and vanilla, they may come back chocolate, vanilla, strawberry, chocolate, strawberry, vanilla, vanilla, strawberry, chocolate, lots of different ways, but really that ice cream cone would be the same. It doesn't really matter what order they're in. So there is a formula for this as well, and that's your combination formula. So the combination of a total of n objects taking r at a time is very much like the permutation formula. N factorial over n minus r factorial, but there is an additional factorial, r factorial, in the denominator. And what that does is it takes care of those combinations that are the same. So chocolate, vanilla, strawberry, strawberry, vanilla, chocolate being the same thing. This last factorial, r factorial, will take care of those duplications because order doesn't matter. So let's actually look at this. If we've got 6 flavors, strawberry, chocolate, vanilla, cherry, orange sherbet, and lime, and we want to make a cone with 3 scoops, how many different ways can we do that? So if we follow the formula, combination of 6, choose 3, and remember, order doesn't matter in the case of ice cream on an ice cream cone, we have 6 factorial, that's the total number of items that we can choose, over 6 minus 3 factorial and 3 factorial. This 3 factorial will take care of the duplications for us. Numerator, 6 times 5 times 4 times 3 factorial. Denominator, 3 factorial times 3 factorial. Now, I can write out 3, 2, 1 and keep going here, but since I know that that's going to be 3, 2, 1, that's going to be 3, 2, 1, and I'm going to divide them out, I don't have to do that. 6 times 5 times 4 over 3 times 2 times 1. That gives me a total of 120 over 6, or 20 choices. There's also a shortcut for this. Now, you can remember the formula. It's not that hard to remember. Total number of objects, factorial. The difference between the objects and the number you want to choose, the difference of that, factorial, and then the number you're choosing, factorial. In the permutation formula, it's just the total objects over the difference. There's no additional r factorial in the denominator. You can also look at it this way. This is kind of just a shortcut way to remember, and you can really see from here. You want to choose 3 objects. 1, 2, 3. Your first choice, you have 6. Now, we're not duplicating. We're not asking for 2 scoops of strawberry. So the second time we have 5 choices. The third time we have 4 choices. Now, to finish it off, to take care of the duplications, you just start with 1 and count up. So if you've got 3 spaces, it's 3, 2, 1. And that will always work as well. So if, for example, if I had 8 choices of flavors and I wanted to pick 2, I could go 8 factorial over 6 factorial, 2 factorial. Or I could go 8 times 7 over 2 times 1. Watch why this works. 8 factorial, 8, 7, 6, 5, 4, 3, 2, 1. That's the 6 factorial. 6 factorial, 2 factorial. These 6 factorials will divide out. I'm left with 8, 7, 2 times 1. So, 2 choices. 8 for the first, 7 for the second. Take out the duplications by counting down to 1, 2 spaces, 2 times 1. So if we've got 6 flavors of ice cream and we want to build a cone that has 3 scoops on it, and the order doesn't matter, that's going to be a combination of the 6 flavors, choose 3. Now, if we cared about the order, if we wanted chocolate, vanilla, and strawberry, and that was different from strawberry, vanilla, chocolate, then we'd be doing a permutation. But because in this case we don't really care, we're doing a combination. Now, if we follow the formula, this would be equal to the total number of choices, 6 factorial, in objects, so we got 6 choices, over the difference between the objects and the number we're choosing, 6 minus 3 factorial, and then to take care of those duplications, since we don't care about the order, an extra 3 factorial, the number of objects that we're taking, factorial, in the denominator. Turns out to be 6 factorial over 3 factorial, 3 factorial. You can write out the 6 factorial, 6 times 5 times 4 times 3, and you could do the 2 times 1, or you could just say 3 factorial. And then these are going to divide out because they're both factors of 3, 2, and 1. So it's really 6 times 5 times 4 over 3 times 2 times 1. That's going to give us 30 times 4, 120 over 6, or 20 choices. So our choices are not as many now because the order of the objects doesn't really matter anymore. Just another quick example of the shortcut. Let's say that you have 10 flavors and you're going to choose 5. You can follow the formula, or you can say, all right, I'm making 5 choices. First time I've got 10, then I've got 9, then I've got 8, then I've got 7, then I've got 6. And then we're going to start with this number and count down. And that's what we do when order doesn't matter. Now, if we were just doing a permutation, we'd just have the numerator. But because we're going to take out the duplications, we need to add in this denominator, starting with the number of objects we're choosing all the way down to 1 factorial. Now, you can use the rules of fraction reduction. 5 and 2 will give you a 10. 4 goes into 8 2 times. 3 goes into 6 2 times. And then you could multiply 9 times 2 times 7 times 2 to get your total. So now we're going to look at 3 examples, and we're going to first decide if we should use the fundamental counting principle, a permutation, or a combination. And then we'll find the answer by applying the appropriate formula. So here are our 3 scenarios. A state lottery requires that the winner select 5 numbers from the numbers 1 through 49. How many ways can these numbers be selected? In this case, order doesn't matter. And in this case, once we've selected a number, we can no longer select it. So this is a combination of 49 objects, taking 5 of them. That gives us 49 factorial over 44 factorial, that is the difference between these two, and 5 factorial. 49 times 48 times 47 times 46 times 45 times 44 factorial over 44 factorial 5 factorial. Now, the reason we don't continue to write out this 44 factorial is it would go from 44 all the way down to 1, and this goes from 44 all the way down to 1. So we've got 49, 48, 47, 46, 45 over 5 times 4 times 3 times 2 times 1. Remember that shortcut? You're picking 5 objects, so you need 5 blanks. They go down by 1 each time. Then to remove the duplications, you take the number of objects you're picking and go down to 1 factorial. Then you reduce that out. 5 into 45 is 9. 4 into 48 is 12. 2 into 46 is 23. 3 into 9 is 3. That leaves me with a 49 and a 12 and a 47 and a 23 and a 3. So there are a lot of combinations here. So we multiply that out with our calculator. That's 1,906,884 different ways that those numbers can come up. And again, order does not matter, and you can only use the number once, and that's what makes it a combination. Now let's look at Part B. For a particular state's license plate, they require 4 letters followed by 3 numbers. How many ways can the license plates be formed? So we've really got 4 choices followed by 3 choices. So I'm going to write out some blanks. 1, 2, 3, 4. And then 3 choices of numbers. Now, we're going to assume that the numbers can be repeated. So you might have A, B, 237. And that's okay. So you've got 26 choices times 26 choices times 26 choices times 26 choices times 10 choices, 10 choices, and 10 choices. And we're saying that each of the choices can be repeated, and we're saying that order does matter. So this is actually the fundamental counting principle. You can multiply this out on your calculator. 26 to the 4th times 10 to the 3rd. 456,976,000 license plate choices. So let's look at the final one, Part C. If there are 20 members in a club and 4 officers will be elected from the members, that's a president, vice president, secretary, and treasurer, how many different ways can these officers be elected from these members? Well, remember in this case that no member can be 2 officers. So if you're elected president, you can't be president and vice president. And being elected president is different from being elected vice president. So the order does matter here. So the order does matter, and you can't have repeated choices. So you can't be both the president and the vice president. So this is actually a permutation of 20 objects taking 4 at a time. According to the formula, that is 20 factorial over 20 minus 4 factorial. So that's 20 times 19 times 18 times 17 times 16 factorial over 20 minus 4 is also 16 factorial. Those divide out. So that gives us 20 times 19 times 18 times 17. And that's basically the shortcut. You've got 4 choices to make. For the first choice, all 20 members are eligible, but then once one is elected, only 19, then 18, then 17. And order does matter here, so we just multiply these together. That's going to give us more choices than we would have if we had a combination where order didn't matter. So 20 times 19 times 18 times 17 is actually, out of those 20 members, over 116,000 choices. There are 116,280 ways to elect the officers of that club.